Okay, AP peeps, welcome back. In this video, we're going to be talking about this idea called the work energy theorem related to section 7-2 in your textbook. So, we know a couple things. Well, first of all, when you're doing work on an object, you're going to be applying a force to it. Now, it's possible that this force produces an acceleration and therefore a change in velocity. And for objects that are accelerating, there were a number of equations that that we dealt with, and one of them was an equation that related velocity to initial velocity along with the rate of acceleration and a distance traveled, or a displacement, as you might say. So there's an interesting thing that we can now do with this, and the interesting thing comes about right here with the acceleration. According to Isaac Newton, any object that is experiencing an acceleration must have a net force applied to it. From Newton's second law, net force is equal to mass times acceleration, and that acceleration therefore is net force divided by the mass. And so what we're simply going to do is, let's see what happens if we take this original equation that we got, I believe was it been in chapter 2, it was quite a while ago, but it's one we're comfortable with. Well, what if we make a substitution, and instead of writing A, what if we write net force divided by mass, just to see what's going to happen. We have our final velocity, initial velocity, both of those are squared. We can't lose track of our exponents. 2, and then here, net force divided by mass. And this is going to be, let's say, maybe instead of a displacement, we can call it just a distance traveled. And the reason for doing that, it sort of is going to match what we're now looking at with this idea of work. If you recall, in the generalized, I've kind of put this off to the side, the generalized equation for work is going to be force times distance times cosine of the angle between those two guys right there. Okay, so got that. And so by having a distance here, well, it seems to match. That's kind of nice. We also see that we have force here in both of these, which is kind of interesting. So how might we kind of rearrange this business to better look like this? Well, I'm going to do something here. I'm just kind of change the way we're thinking of this to simplify it. Let's see what happens. If the angle between the force and the distance traveled is 0, in other words, if the force is in the same direction as the distance traveled, well, the cosine of that angle, well, the angle will be 0 and the cosine would be 1. So our work equation kind of simplifies to this in that kind of ideal situation. Awesome. So we need a force times distance sort of in this equation. And so with some handy-dandy rearranging, I'm going to be looking at, I'm just going to bring my force and my distance to the other side. And I want to see what's going to happen over here. Well, I'm going to have a final velocity squared minus an initial velocity squared, and I'm then going to have to be divided by 2, and I'm going to have to be multiplying by m. Dividing by 2, well, we can say instead we're going to multiply by 1/2, same thing, and then I will have multiplying by mass, and I'm going to have my final velocity squared minus my initial velocity squared, right? Well, what's interesting here is we see that this business now is equivalent to work. And since we're dealing with net force, this is equivalent to the total work done on an object. Well, but the total work done, if it's done by the net force, it's producing a change in the velocity of the object. We see that change taking place right here in the equation. And this doesn't really simplify any. You can't say that it's delta v squared. The math doesn't jive. But we have this, now. Okay. And this is an important thing. Now, sort of aside from that, what is going on here? Well, we have 1/2 times mass, and we sort of have velocity squared. I mean, there's more going on here. We have a difference of squares, but new idea here, not related to the same sequence of thinking going on. New idea. This idea of 1/2 the mass of an object times the velocity of the object squared. Well, this is given a name. This is kind of special in physics. And this is now called kinetic energy. Okay. So if you were to look at the situation just a little differently, we're gonna kind of expand this. Instead of simplifying it, we're gonna separate things out just a little bit and come back to this idea of what work does to the kinetic energy of an object. So here we go. Page 2. When we do work on an object, then what we have essentially is, if I take this line in this equation here, and I actually distribute the 1/2 m to both of these two terms. All right, so it's going to be 1/2 m times final velocity squared minus 1/2 m times initial velocity squared. And looking at it this way is beneficial because what I can do is come back to this idea, this new idea called kinetic energy now. And I can say to myself, well, look, kinetic energy is just this sort of general thing where I take the mass of an object, I take its velocity squared, multiply, and then take half of that value. That tells me how much kinetic energy the object has. So what's going on here? This is how much kinetic energy the object has in a final state after a change takes place. So you might say that this is kinetic energy final. This is the amount of kinetic energy the object would have before we did any work on it. It has a mass and it has a velocity before we do some work. So this could be the kinetic energy initial. So we have created a change in the kinetic energy. Final minus initial anything is just a change in that quantity. We've created this change in kinetic energy by doing work on the object. Generally speaking, when we talk about kinetic energy of an object, it is due to the velocity that the object has. Yes, mass is involved. If an object has more mass compared to another, and they're both traveling at the same velocity, the one with more mass will have more kinetic energy. But most of the time, you will encounter situations where the object's mass is constant and the velocity will be changing. And in this class, we're going to only look at situations, at least I believe, we're only going to look at situations where the velocity is changing but the mass is constant. You can imagine a situation where mass would change. For example, if you're going to launch a rocket, try to put a satellite into orbit. As the rocket is flying upward away from the surface, it's burning up some of its fuel as time goes by. And as it burns the fuel, it becomes lighter. It has less mass. So you have a changing mass, and you also have a changing velocity. It's a much more complex situation. We will not be looking at that. For our work, we're going to just kind of look at situations where mass will be constant. And in order to talk about a changing amount of kinetic energy, we'll talk about a change in the velocity of an object. Okay. So that's it. This right here is the work energy theorem. Pretty straightforward. What you will have to do from time to time is work back from this sort of general statement and say, okay, what was the initial velocity? What was the final velocity? Or maybe you're asked to find if we do a certain amount of work, and you know the initial velocity, what would the final velocity be after doing that much work? You can imagine all kinds of questions. It's almost like taking this line in the equation and saying, well, what's your unknown going to be? And I can write a new question to try to solve for that unknown. Okay. There's some interesting things, though. You can see that the relationship between the work done and the velocity, or even here, in simple terms, the relationship between the kinetic energy and the velocity is not a linear relationship. You have this exponent here. And so it's easy to deal with, but you have to ask yourself, if you're just going to talk about the kinetic energy of an object, so let's say you're going to double the velocity of an object. What happens to the kinetic energy? Well, because you're looking at this simple relationship, kinetic energy is 1/2 mv squared, and you're going to double velocity. When you do this, when you write this down, or even just doing it in your head, you have to think mathematically here. You have to think about doubling velocity. All right, but then this is how you have to represent this mathematically, that the 2 will also be squared. And what's the overall effect when you double the velocity? You have to also change this side. What happens to kinetic energy? Do we just put a coefficient of 2 in front of k? The answer is no, because the overall effect on this side is that the 2 is squared, and so you have 4 times the amount. You could ask yourself, well, if the velocity is halved, if it's cut in half. So you take your kinetic energy, you look at this, and you're going to say to yourself, well, I now have 1/2 my velocity. 1/2 squared is going to be 1/4. And so to maintain equivalence here, so I don't kind of violate the rules of math and break the universe and all that, this is going to be 1/4 the amount of kinetic energy if the velocity is only 1/2 the original value. And I think those kind of things, those kinds of relationships are pretty easy to recognize. Don't lose track of your exponents, please. Losing track of an exponent is terrible. I'm going to look at you funny if you do, and make all kinds of crazy faces. So don't make me do that. Ladies and gentlemen, that is the work energy theorem in a nutshell. And we'll look at some examples in class. Thanks for watching.